Welcome back. Now we're going to be focusing on a cantilever beam with a UDL, or uniformly distributed load. Let's find the reactions and let's find the internal forces. Let's get to it. So before I focus on finding the reactions, I'm just going to replace this fixed support with the reaction forces. So AX, AY and MA. As we mentioned quite a few times, in a cantilever beam, the reaction forces AX, AY and MA are completely independent of each other, and therefore we don't have any equations with two variables. We can solve them in any order that we want to. So I'm going to start off by summing the forces in the x direction, with this being my positive x. So I've got AX plus no other forces, so AX works out as 0. Then I'm going to move on to the sum of forces in the y direction, with this being my positive y direction. In this case, I've got AY, and then I've got this UDL, so minus 5 kilonewtons over meters times 4 meters. And we can see here that when we multiply that uniformly distributed load by the distance, we actually get the area, and the area is the force. Okay, nothing else in the y direction, so that equals 0, and therefore AY works out as 5 times 4, so that is 20 kilonewtons. And the last thing that I'm going to do is the sum of moments around point A equals 0, with this being my positive direction, and in this case I've got MA, that support reaction for the moment, and then I've got the uniformly distributed load. So that gives me a negative moment, right? It gives me a clockwise moment. So minus 5 times 4, that gives me the force. And the distance is 4 over 2. Okay, so the distance, just a reminder, is always the distance from the centroid of the shape of the UDL, which is in the middle for a rectangle, to wherever we're looking for moment. So in this case, the moment is just here at A, and therefore that is the distance, 4 over 2. And that is all I've got contributing to moment at A. So that equals 0, and MA equals 40 kilonewton meters. Now I am going to draw what I found. So I found that AX was 0, so I can just get rid of that. The value for AY was 20, and that worked out as positive, so the direction that I assumed is correct. And MA worked out as 40. Again, that came out as positive, so the direction that I assumed is correct. Now, before I move on in this case, I do want to do a check. Okay, so let's see how we check that that reaction is correct. And to check, I can do any other equation of equilibrium. In this case, I'm going to check the moments at B and know that that needs to equal 0. So if I do moments at B, I've got MA, right, the moment from the support. I've also got AY, so minus AY, that reaction force, times 4, the distance. And I've got a positive contribution from that UDL, so plus 5 times 4, that is the force, and then times 4 over 2, that is the distance, and that should equal to 0. MA we found is 40, AY is 20, so that's 20 times 4, and this contribution from the UDL is 40, and so I've got 40 plus 40, that gives me 80, and then I've got minus 80 here, and that equals 0, which means that my check is complete. So now that we've found the reactions and we've drawn our free body diagram, we are ready to find those internal forces. Okay, what we need to do now is make a cut, make sure that everything is in equilibrium, and find and graph those forces. Let's do it. Okay, and now that we have the reactions, we've drawn them on our free body diagram, we are ready to solve the internal forces. Now we can see here that we've got a lot happening at A, we've got all those reactions, and at B, the UDL ends, so I'm going to do a cut somewhere between A and B. Nothing else changes apart from the UDL, and doing this cut will allow us to figure out how that UDL influences the internal forces. Now, the other thing that I've done in preparation is under this beam, I've just drawn out places to draw my internal forces. So N for the axial force, S for the shear force, and M for the bending moment diagram. You can see that stuff happens along A, stuff happens along B, and in between I've got my UDL. Now to find the internal forces, I am now going to have to draw my cut. It's going to look something like this. So this is part of my beam. I'm going to start from here, and this is where my X will go. I need to put those reaction forces that I found, so 20 and 40. I've got whatever part of that UDL I can cover over X. And now that I've created the cut, in order for all this to balance and be in equilibrium, I need to add those internal forces. So N, which might be a function of X, S, which might be a function of X, and my bending moment M, which might also be a function of X, all of these drawn in what I've agreed as the positive directions of my sign convention. So we'll start off by summing the forces in the X direction, with this being my positive X, and I can see that I only have nx in this direction, so nx equals 0, and I can straight away draw that on my diagram. Just 0 from A to B, no change. Moving on, I'm going to sum forces in the y direction, with this being my positive y, and if I do that, I see that I've got minus the shear force at the cut, Sx. I've got positive 20 from the reaction, and I've also got that part of the UDL. Now this is in the negative y, so minus and 5 times x. That'll give me the force. Remember, whenever you have a distributed load, the actual load itself is the shape under that UDL. So in this case, I've got a height of 5, that's my load, and a distance of x. So 5x gives me the total force, and that equals 0. There's nothing else in the y direction. So S, my shear force, is 20 minus 5x. And I can see here that this is a linear line. I'm interested in what's happening at point A, so when x equals 0, and at point B, when x equals 4. When x equals 0, I see that I get 20 kilonewtons, and that's a really good sign, right? Because that is what my reaction force was. And when I'm standing exactly at point A, that UDL hasn't really influenced yet, and therefore 20 kilonewtons is the shear force at that point. When x equals 4, I get 20 minus 5 times 4, so 20 minus 20, that gives me 0. And once again, that makes sense, because when I'm standing at point B, that UDL hasn't started to influence yet. I really have 0 shear at B. And so I can now straight away draw on 20 here, 0 here, and as we already mentioned, this is a linear line, and therefore it'll look like this, with 20 here, 0 here, and overall positive in our sign convention. And the last thing that I want to do is the sum of moments. So I'm always going to sum those moments at the cut. So sum of moments at the cut. And the reason for summing them at the cut is if I've miscalculated anything at the cut, say my axial force or my shear force, it's not going to influence. So what do I have at the cut? I've got that moment, mx, right? That's the internal moment at the cut. I've got a moment, positive moment at 40 from the reaction. I've then got that reaction force of 20, creating a negative moment at the cut times the distance of x. And I've also got the UDL contributing a positive moment. 5x, as we said, gives me the force, and x over 2 gives me the distance. And just a reminder here, when I'm calculating a UDL, the force is the area, so that gives me the force, and the distance is always going to be the distance from the centroid, in this case the middle, to wherever I'm figuring my moment around. So here, here, it might be, in this case, here, right, to the end of that UDL. So therefore, if this is x and this is 5, this is x over 2. Nothing else contributes to the moment, so I can now equate that to 0 and rewrite that equation with the internal moment on one side. So I get minus 2.5 x squared plus 20x and minus 40. And we can see already here that this is a parabola. so whatever I draw has to be parabolic. Let's check out a few points. Let's check what happens when x equals 0 and when x equals 4, so at point A and point B. Let's also see what happens at the middle when x equals 2. So when x equals 0, you can quickly see that I get minus 40 kilonewton meters. Once again, that makes sense, right? Because that is the reaction moment. When x equals 4, I can see that I get 0, which again makes sense. That's a free end. The moment should be 0. And when x equals 2, I can calculate and I'll find out that this works out as minus 10 kilonewton meter. Now, what does that minus mean? Well, it means that I cut and I assumed that my moment was in this direction. It is in fact not in that direction, right? We've just found that it's minus, which means it's really in this direction. And that means it's pulling on the top and pushing on the bottom. Where it pulls, it elongates and creates tension. Where it pushes, it shortens and creates compression. So I draw on the tension side, meaning I know that I need to draw on this top side here. So if I go back to my graph, I have 40 here. In the middle, I've got 10, and here, and at the end, I've got 0. I know that this is a parabola, so it's going to look something like this, with this being 40, this being 10, and overall what I would call a negative moment. And that's the internal forces, all calculated, graphed, and written with equations that will allow us to find the internal forces wherever we might seek them. So, once again, we drew a free body diagram, found reactions, and calculated internal forces. This time for cantilever beam with a UDL. I hope this has been helpful, and I hope you join me for some more structural engineering. Bye for now.